Hello everyone, welcome back to mkbnTech. Everything you are seeing now, that's not a demo environment. That's a real e-commerce platform running on real Azure infrastructure across three separate environments. And every single thing that is happening, the deploy, the promotion, the merge request, happened because of one Git push. By the end of this video, that's not something you will have watched me do. That's something you will have built from scratch and actually understand, not copy pasted, understand every single piece of it. We are going to provision real infrastructure on Azure with Terraform. We are going to build, test, and security scan all our images with GitLab CI. We are going to deploy them the actual GitOps way with Argocd, not scripts. And we are going to promote through dev, UAT, and prod with Kargo. Watching one real code change travel automatically all the way to a human approved production release. Here is what makes this video different from most GitOps tutorials you have watched. I'm not just going to show you how. Every single tool we install, I'm going to tell you the actual problem it solves and why I picked it over the obvious alternative. Because copying commands off a screen doesn't make you a DevOps engineer, understanding why the command exists does. So grab a coffee. This is a long one on purpose. Let's go build something real. Here is what we are building, top to bottom, right now before we touch any tooling. 4 services, a Node.js storefront, a Python catalog service, a Go recommendation engine, a Java review service backed by a real Postgres database. 4 different languages, 4 different runtimes, each one talking to the other over plain HTTP. This is what we call a polyglot microservice architecture. And I want to be upfront with you. This isn't me picking 4 languages to show off. This is genuinely how a lot of real mature engineering organizations look. Different teams, different strengths, different tools for different jobs. And that variety is exactly what makes the platform side of this interesting. Because whatever we build has to work for a Node app, a Python app, a Go app, and a Java app, all at once without 4 different playbooks. 3 repositories, and this split is deliberate, not incidental. The app service repo, that's where the 4 services actually live, code and Docker files owned by developers, changing constantly. And we have 2 more repos, env-config-gitops and AKS-infra. That's the platform team's repo. Helm charts, environment configuration, and Terraform manifests, changing rarely, mostly by automation. We will get into exactly why that split matters later, but I want it on your radar now because you are going to see us clone 2 different repositories throughout this video, and I don't want that to be confusing when it happens. 3 environments, not 3 folders in one cluster. 3 actual separate Azure Kubernetes clusters, plus a 4th dedicated management cluster that runs nothing except our deployment tooling. A change has to earn its way from dev to UAT to prod. And we are going to build that exact mechanism that decides when it's earned that automatically, where it's safe, and gated by a real human approval where it isn't. And the toolchain at a glance, before we go deep on any of it, Terraform builds all that infrastructure from code, so it's reproducible, not something living in one person's memory of what they have clicked in a portal. We are going to use GitLab CI for builds, tests, and security scans every image before it's allowed anywhere near a registry. Argocd watches our GitOps repo and makes every cluster match what Git says continuously. That's the actual meaning of GitOps. And it's less obvious than it sounds, so we will spend real time on it. And Kargo, the tool most of you haven't used yet, and honestly, the most interesting one in this video. Sits above Argocd and decides when a change is allowed to move from dev to UAT to prod. That's the whole system. 4 services, 2 repos, 4 environments, 4 tools, each with exactly one job. Everything from here forward is just filling in that picture, one real working piece at a time. But before any of that, every good system exists to solve an actual problem for an actual business, and ours is no different. So let's meet who we are actually building this for. Meet the TrailHead Supply Co., a hiking and outdoor gear retailer with a handful of physical stores and loyal customer base of people who actually use their gear on actual trails. Real business, real inventory, real revenue. Every sale is capped by whoever can walk through their front door. Someone 3 states away who wants their boots simply can't buy them. Their competitor sells online, TrailHead doesn't. So leadership makes the call, we are going online, and hires a development team who build exactly the platform we just walked through. The dev team build the app, it works, it runs on someone's laptop, and now that's where you come in. You are joining TrailHead as their DevOps engineer, and your job is not to write more application features. Your job is to answer this question. How does this application go from a developer's laptop to real customers safely, repeatably, and without you personally being the bottleneck? That's the whole job actually when you strip away the buzzwords. Let's define what production ready actually means here, concretely, because it's not a vibe, it's a checklist. Infrastructure that's reproducible. If our Azure region got wiped tomorrow, could we rebuild dev, UAT, and prod from a single command? If the answer is no, we don't actually have infrastructure. We have a pet we are keeping alive by hand. A CI pipeline that catches problem before they ship. Not just does it compile, but does it have a non-critical vulnerability sitting in a base image? Deployments that are declarative, not imperative. Nobody should ever run kubectl apply from their laptop against production, ever. The cluster should describe itself in Git, and something should make reality match that description automatically. A real promotion story. Dev is where everything moves fast and break. Prod is where a human being should look at what's about to change and say yes, ship it on purpose, not by accident. And a secret that are never sitting in plain text in Git repo, no matter how tempting it is at 11 p.m. when you just want the demo to work. TrailHead supply code developers are using GitLab as their source code management system. They already granted access to app service repo. I need to add an SH key for GitLab to verify my identity and securely authorize access to private repositories without requiring a password every time. I have already generated an SH key using sh-keygen command. I will go ahead and cat the public key. This is my public key. I will copy the public key, head over to our GitLab instance, click on the profile icon, and select Preferences. Next, I will navigate to Access and select SH keys. And we're going to add a new SH key by selecting Add New Key. I will paste the SH key and leave the title to mkbnTech at mkbn, and I'll click on Add Key. And we have successfully added an SH key. Now let us head back to our GitLab instance and try to clone the repository. I'll click on Groups and navigate to TrailHead Supply Co. and select our app services repo and click on Code and select Clone with SH. Let's head back to our terminal. We'll run git clone, then I will paste the git URL and hit enter. This will go ahead and clone the app services repo to our local. And the repo is successfully cloned to our local. If I run ls, I can see we have app-services, and we can go ahead and open the app services using a code editor like VS Code. I will run code space app-services. This will go ahead and launch VS Code. Before we run anything, I want to actually read this code base with you. All 4 services and the Docker files that package them. Because watching a demo work is a lot less useful than understanding why it works. And once we get to the GitLab pipeline at the end of this segment, you will recognize exactly what it's doing because you will have already seen the code it's building. We will go service by service in the order a request actually flows through the system. The storefront first, since that's the front door, then the 3 backend it talks to. Let's start. I will navigate to services and click on UI services and open server.js file. This is our BFF backend for frontend. That term matters, so let's be precise about it. This service doesn't own any data, it doesn't have a database. Its entire job is to render HTML and fan out to the three backend services to assemble each page. Look at the comment right at the top of the file. This is deliberate documentation, not an accident. No page ever talked to the backend directly. That's a rule the front end, the browser, never violates because it never gets the chance to. Every product page you will see in a minute is server rendered, which means the browser gets finished HTML, not a pile of API calls it has to orchestrate itself. Pre-environment variables, pre-sensible localhost defaults. This one detail is what makes the exact same code work unmodified whether it's running under Docker Compose on your laptop or inside a Kubernetes pod in production. Only the value of these variables changes driven by whatever Helm charts deploys it. Nothing in this file needs to know or care which environment it's in. Here is the interesting part, the product page. A single page load on this site actually has to call three separate services and combine the results. Two things worth stopping on. First, these three requests fire in parallel, not one after another, using promise.all a few lines down. If we call them sequentially, a page load would take the sum of all the three services response times instead of the slowest one. Small difference on your laptop, a real felt difference once these are real network calls between separate pods. Second, look at that dot catch on the recommendation and reviews call specifically. If either of those backend is slow or briefly unhealthy, that request fails gracefully into an empty result. The page still renders just without recommendations or without reviews instead of crashing the whole page load. That's a deliberate resilience choice. A product page with no recommendations is a worse experience than it could be. A product page that won't load at all because one non-critical backend hiccup is a much worse one. One more thing before we leave this file because it's genuinely worth calling out. This service exposes real Prometheus metrics, not a placeholder LCheck pretending to be one. That's a histogram tracking actual request latency broken down by the route and status code on top of Node's own default process metrics, memory, event loop lag, garbage collection. This is the real thing our service monitor in the GitOps repo is built to scrape. We will see that data land in Grafana later in the series, but it's worth knowing right now. This isn't a demo stub, it's a genuinely production-shaped observability sitting in the same file as everything else. Quickly on the templates themselves, let's navigate to views and open home.ejs. This is server-rendered EJS, not a client-side framework, which keeps this service simple on purpose. No build step, no bundler, no client-side state management for a page that doesn't need any of that. A couple of details worth pointing at because they're not just decoration. The tiny inline script sitting in the head before anything else loads is what stops you from seeing a flash of the wrong theme on page load. It runs before the browser paints anything, reads a saved preference, or falls back to the system's own preferences and sets the theme immediately. Small detail, but it's exactly the kind of thing that make an app feel finished instead of just functional. Next, let us take a look at the Docker file really quick. It's a single stage build. Node doesn't need any separate compile steps the way Go or Java do, so there is nothing to build and throw away here. A few things worth pointing out regardless. -- omit is equal to dev keeps dev dependencies out of the final image entirely. The user node, the base image, ships a non-root user. Specifically for this means this container never runs as root, which matters the moment anyone asks, what can an attacker do if they get code execution inside this container? And there is a real health check instruction hitting this same service own /health endpoint, which is what lets Docker and later Kubernetes own probes actually know if this thing is alive, not just running. Now, the catalog service. I will navigate to catalog service, apps, and open main.py. The catalog service is built using Python and Fast API. This service owns exactly one thing, product data. No other service is allowed to know what a product looks like except through this once API. That's deliberate, and it's the same idea as the UI never talks to a database directly, just one layer over. Clean, small, does one thing. Fast APIs type hints double as request validation here. That's path parameters typed as a string. And Fast API handles the parsing and the Open API schema generation from that signature alone, which is a big part of why this stack is genuinely pleasant for a small internal API like this one. And let us understand the instrumentation. Same story as the UI service. This isn't hand-rolled. One library wired in near the bottom of the file gives this service the same production ship metrics the other have: request count, latencies, status code breakdowns, with essential no custom code. Now let us switch our attention to the Docker file. Same shape as the UI services Docker file. Same reasoning. Slim base image to keep the surface area small. The -- no -cache dir, so pip's own download cache doesn't load the image, and user is set to 1000, a non-root numeric UID this time rather than a named user, since the Python slim image doesn't ship 1 for us the way Node does. Same outcome either way, this container never runs as root. Next, let us review the recommendation engine. I will navigate to recommendation-services directory and open main.co. The recommendation engine is built using the Go and deliberately no framework, just the standard libraries on net or HTTP. For a service this small and this stateless, pulling in a web framework buys you almost nothing and costs you a dependency you now have to keep patched. This is the recommendation logic in full. It's intentionally simple: same category score highest, shared tags, and a small bonus, and a small deterministic jitter breaking ties so that ordering doesn't feel robotic. This isn't meant to be a real recommendation algorithm. It's meant to be a real service boundary doing a real job. Notice it doesn't own any product data itself. It calls the catalog service to get it the same way the UI calls this service. Every service in the system only owns the one thing it's actually responsible for. Next, let's understand how the metrics are handled in this. So if we scroll down, we have the max.handle, one line to register the handler, and the official Prometheus Go client library takes care of the rest. Same instrumentation story a third time in a third language, because Prometheus client libraries exist for every major ecosystem, specifically so this pattern stays consistent regardless of what a given service is written in. Let's review the Docker file. This one's genuinely different from the other three, and it's worth understanding why. We have two stages. The first build has the full Go toolchain, compiler, shared library, everything need to produce a binary. The second stage starts completely fresh from a distroless, an image that contains almost nothing. No shell, no package manager, no ls, no cat, none of the usual Linux userland. Just the one compiled binary copied in from the build stage and NFC library support to run it. You may ask, why go this far? Because Go compiles to a single static binary. It genuinely doesn't need an operating system's userland to run, just a kernel to run on top of. So we don't ship one. If someone ever compromised this specific container, there is no shell to drop into, no package manager to pull tools with. The attack surface is about as small as running process can realistically be. We have set the user to 65532:65532. On top of that is distroless own convention for run as non-root. And finally, let's take a look at the review service. I will navigate to review service directory. Inside, we have the required Docker files along with that source directory, which contains Java directory, the controller, model, repository, etc. The review service is built using Java Spring Boot, and the one service in this system with real persistent relational data behind it. Every other service is effectively stateless, but reviews are exactly the kind of data you need to keep correctly forever, which is why this is the one place we reach for real database instead of an in-memory structure. I will navigate to repository.java. This is Spring Data JPA doing something genuinely worth pausing on. That's the entire implementation. One interface, one method signature. Spring reads the method name itself, find by product ID, ordered by created at, and generates the actual SQL query behind it at runtime. Next, let's review the application.yaml. And here is the fourth service version of the same metric story. Spring Boot actuator with micrometers Prometheus registry pulled in as a dependency, poses a /actuator/Prometheus endpoint with essentially zero custom code. 4 services, 4 different ecosystems, and every single one of them ends up with the same shape of production-grade observability. That consistency across genuinely different stacks is one of the things that make this feel like one coherent platform instead of 4 unrelated projects glued together. Next, the Docker file. Multi-stage again. Same underlying reasoning as the Go service adapted to Java shape. The build stage has the full Maven toolchain and every compile time dependency. The runtime stage only has a JRE, a Java runtime, not the full JDK, plus the one compiled .jar file copied across. We don't need a compiler in the container that actually running in production. We don't ship one. And notice the small details in that dependency :go-offline line. Before source even gets copied in, that's a deliberate Docker layer caching trick. Dependencies resolve once and get cached, so a source only change on your next build doesn't force Maven to re-download the entire dependency tree. Before we provision a single cloud resource, we do the thing every good engineer does first. We run it on our own machine. If it doesn't work here, it is not going to magically work in Azure. This is our first repository called app-services. This is where the developer actually code lives. As a prerequisite, ensure you have Docker and Docker Compose installed on your dev machine. And let us go ahead and run the docker compose up --build command. This will go ahead and bring up our stack. While that's building, worth calling out what docker compose.yaml is actually doing here. It's not just starting for containers, it's starting a fifth one too, a real Postgres container for the review database, because we want local development to mirror production as closely as possible. If review service only ever talked to an in-memory database locally, it would ship a bug to prod the very first time real Postgres behave differently than the fake one. We don't want that gap. So all our services are up and running. Let's go ahead and access our website using the localhost port 3000. I will head over to a browser, and in a new tab, I will open http://localhost port 3000. Let's hit enter. And there it is. This is TrailHead storefront running entirely on your laptop. All 4 services talking to each other over Docker's internal network, exactly like they will in Kubernetes. This is our product grid coming from the Python catalog service. Let us select one of the product. And if we scroll down, we also have the recommendation down here. And that's the Go service actually calling the catalog service itself to build that list. And down here, reviews coming from Java and a real Postgres row underneath it. Let's actually post one. I will add the title. Then I will rate it as 4 solid. I will say amazing backpack. And I'm going to post the field report. And that write just went through Spring Boot into Postgres and came back out onto the page. Full round trip, all local, zero cloud dependency. The docker compose.yaml file also brings up our monitoring stack, which includes Prometheus, Grafana, Loki, and Promtail. We can access the Grafana dashboard by hitting the localhost port 3001. Let us head over to our browser, and in a new tab, I will open http://localhost port 3001. Let's hit enter, and this is the Grafana homepage. Let us click on dashboards. I have created a custom dashboard for our TrailHead microservice monitoring. If I open that, we can see there are 4 services: the UI service, catalog service, recommendation service, and review service. We're able to see the metrics. We can also click on explore, and instead of Prometheus, we can choose Loki and query the logs. In the labels filter, I will select service_name, and let us choose one of the service and click on run query. And we could see the logs are streaming successfully, and it is able to get the health and the status is okay. And this setup would help us to customize our queries based on the requirements and test it locally without shipping it to actual monitoring stack. Before we go ahead and build the actual infrastructure on Azure using Terraform, I want to show you something I have discovered recently. Imagine you want to share this with one of your colleagues working remotely. This is completely a local setup, so you are running the application using the Docker Compose up and able to access your application with port forward, which is localhost 3000 or 3001. Support for port forwarding is built into VS Code via Microsoft Dev Tunnels, so no extension required. When running a local web service, you can use this port view to make the service accessible to others over the internet. Let me show you how to do that. So let me open another tab. So currently our application is running. What I will do is I will go ahead and click on ports and I will click on forward port. Our application is accessible via port 3000. So let us go ahead and do that. So it is starting port forwarding. If you're not logged into GitHub, it will prompt you to log in. I'm already logged in. As you can see that I'm using my mkbnTech GitHub account. So it has created a publicly accessible link. So we can copy this. And if I head over to a browser in a new tab, I will open this, which is a public URL. And now people can access your application like it is running on their own laptop. How cool is that? Every tool we pick in this video exists to satisfy one or more of these, not because it's trendy, because it solves a specific named problem on this list. Let's meet our first tool, Terraform. The problem is someone clicks around the Azure portal, creates an AKS cluster by hand, gives it a name, forgets exactly what setting they picked. 6 months later, nobody can tell you why UAT's cluster has a different node size than devs. Nobody can recreate it. That knowledge lives in one person's mouse clicks and it's gone. And solution to that problem is Terraform. You write down in code exactly what infrastructure should exist. This resource group, this AKS cluster with this node pool, this Azure Container Registry, this Key Vault, and Terraform's job is to look at Azure, look at your code, and make Azure match the code. Run it again next month, nothing changes because reality already matches. Change the code, run it again, only the difference gets applied. And the next obvious question is why Terraform and not say Bicep or an ARM template, both of which are Azure native? Two honest reasons. One, most real organizations are in single cloud forever, and Terraform's provider model means the same mental model, the same HCL syntax, works whether you're on Azure, AWS, or GCP. Two, the state file and plan or apply workflow gives you a genuine, readable, here is exactly what's about to change preview before anything happens, which is exactly the kind of safety net you want before you touch anything that says prod on it. Here is what we are about to build, not one cluster, but 4. Let's start with the whole picture before we zoom into any one piece. We have 3 separate copies of the same environment, namely Dev, UAT, and Prod, sitting in 3 separate Azure subscriptions. Think of a subscription as a separate locked office suite in the same office building. Dev is where you experiment, and it is fine if things break. UAT, the user acceptance testing, is a rehearsal space that looks like the real thing, but Prod is the real thing, real customers, real consequences. Each of those 3 suites contain an identical set of furnitures, a Kubernetes cluster, a vault for secrets, plus one more thing that's shared across all 3 rather than duplicated, which we will get into in a moment. What differs between the 3 isn't the furniture, it's the size of it and how tightly the doors are locked. At the very top of the diagram, a pipeline in GitLab is what actually building all of this. And notice, there is no key or password floating around anywhere. We'll come back to that. It's one of the most important ideas in this whole project. First, let us go ahead and create a repository in TrailHead supply code group to host our Terraform config files. I will click on Create Project, and I will create a blank project, and I will name this Azure-Infra. And we will keep the project visibility to private, and we will go ahead and click on Create Project. The Azure Infra project is successfully created. Next, let us go ahead and push our local changes to the remote repository. As a DevOps engineer, you have already developed all the required Terraform configuration files to provision the infrastructure on Azure. Next, you need to go ahead and push this to the remote repository. If we head back to the GitLab repo, and if we scroll down, we can push an existing folder. So you need to navigate into the folder, then you need to initialize it as a Git repository. So I'm currently already inside the Azure Infra repository. Let's go ahead and run the git initialize command. Next, let us go ahead and add the remote origin by running the git remote add origin and specifying the repo URL. Next, let us go ahead and run git status. So we have the following files. Let us go ahead and do git add dot to add the files. And we're going to do git commit -m and we're going to say initial commit. And all our files are added. Let's go ahead and do a git push -- set upstream origin main and let's hit enter. All our local changes are pushed to the remote repository. Let's head back to our repository and refresh the page. And we should see all our config files exist in our remote repository. Before we open any files, one idea has to click. Terraform doesn't run commands, it describes a destination and figures out the route itself. You write a file that says, I want a Kubernetes cluster with these settings. Terraform compares that description to what actually exists in Azure right now, works out the differences, and show you a plan, a list of what it's about to add, change, or destroy before it touches anything. That's the single habit to build as a beginner. Always read the plan. It's the difference between I think this is safe and I know this is safe. When you open the modules directory, you will find 6 smaller folders. Each one is a reusable blueprint for exactly one kind of a furniture. And critically, none of them know anything about dev, UAT, or prod. They just know how to build their one thing, however they're told to. First, the resource group. This is the smallest one, just a labeled folder in Azure that everything else for that environment lives inside. When we delete an environment later, this is the folder we throw away and everything inside comes with it. Next, networking. This bundles a virtual network. Think of it as a private road system inside our office building, split into 2 neighborhoods. One road leads to where the Kubernetes node lives, the other smaller road is reserved for private connection to sensitive services, which we will use in a moment. This is the big one, the Kubernetes cluster itself. And here is a detail that matters. Inside every cluster, there are 2 kinds of workers. The system pool is like the building's permanent front desk staff, always on, never given extra jobs because the cluster's own critical plumbing runs here, and we don't want it to competing for resources with your applications. The user pool is everyone else, the actual staff running your applications, and this pool can grow or shrink automatically based on how busy things get. That's auto-scaling. More customers, more staff, white afternoon, staff go home. Nobody has to watch dashboard and manually adjust it. Key Vault is exactly what it sounds like, a safe. Passwords, connection strings, certificates, anything an application needs but should never be typed into a config file in plain text lives here instead. Now, here is that one shared thing from earlier. The container registry is a warehouse where you package an application into a container image. It has to live somewhere before Kubernetes can run it. But unlike the other furnitures, there's only one warehouse for all 3 suites, not 3 separate ones. Think of it as a shared loading dock for the whole office park, rather than a private stockroom in each suite. Every cluster is given its own key to that one warehouse, so dev losing its key doesn't affect prods, but they're all pulling from the same shelves. And notice, again, no username, no password is configured for pulling images. We will explain exactly how that works in a few minutes. And finally, the log analytics, the security camera, and the logbook together. Every pod that starts, every error that gets thrown, flows here. So when something goes wrong at 2 in the morning, there is a record to look at. So if the modules are blueprints for furniture, the environment folders is where we actually furnish a room. You open environment/dev and you will see one file called main.tf that calls 5 of those 6 modules in order and wires their output into each other's input. The Key Vault ID goes into the cluster module and so on. The 6th module, the registry, isn't called here at all. It lives in its own environment/shared folder built once and dev just point at it by ID. Here is the part that makes this design worth learning. Environment/UAT and environment/prod calls the exact same modules in exact same order. The only thing that changes between the 3 is a file called terraform.tfvars, a simple list of settings. Dev gets a small, cheap virtual machine and publicly reachable vault. because convenience matters more than lockdown while you are experimenting. Prod gets bigger machines spread across multiple physical zones for resilience, and that vault is sealed off from the public internet entirely. Same blueprint, different dial settings, that's the whole idea. One more idea, and it's a subtle one. How does Terraform even know what it built last time, so it can compare against it next time? It keeps a file, the state file, that's essentially an inventory list of every real resources it's responsible for. Before Terraform does anything, it reads this list first. That list has to live somewhere everyone and every pipeline run can reach reliably, which is why one small storage account created once holds three of these lists side by side, one for dev, one for UAT, and one for prod. Separate list, so a mistake while working on dev can never touch prod's inventory by accident. Let us go ahead and provision a storage account along with a container to store our Terraform state files for dev, UAT, and prod. If we head back to our VS Code, in Azure Infra, we have a directory called Bootstrap. And if I open the main.tf file, this basically creates three resources, an Azure resource group along with Azure storage account and an Azure storage container. Let's go ahead and provision this. Before we can run the Terraform commands against our Azure infrastructure, you need to install Terraform locally on your laptop. In my case, I'm running Terraform version 1.15.8. Also, make sure that you have installed AZ CLI because we will use AZ login command to authenticate with Azure. In my case, I'm running the AZ CLI version 2.87.0. Next, let us run AZ login command on our laptop. This will open a new page. Go ahead and sign in to your Microsoft Azure account using your email address or phone number. If I head back, I can see that it's displaying my subscription name along with the subscription ID and the tenant. I will go ahead and hit enter. So I'm successfully logged in. You can also run AZ account list command to verify that you have logged into your Azure account. If you are new to Terraform, remember these three commands: Terraform init, Terraform plan, and Terraform apply. Let us navigate into our Bootstrap directory, which contains our Terraform config files main.tf, output.tf, and variables.tf. Let us run Terraform init and hit enter. Terraform init is pulling down the Azure provider, the plugin that actually knows how to talk to Azure APIs on Terraform behalf. And on the left-hand side, you can see it has created the .terraform.log.html. Next, we're going to run the Terraform plan against our subscription ID. Let us run Terraform plan, and we need to specify the subscription underscore ID, and this is my subscription ID. If I head back to variables.tf, we have a variable called subscription underscore ID, and the type is string. Let's go ahead and hit enter. This is the step I want you to really pay attention to, because this is Terraform's old safety promise in one command. Nothing has happened to Azure yet. This is just Terraform saying, here is exactly what I'm about to create: resource group, storage account, a container. Read through this like you would read a diff on a pull request, because that's exactly what it is, a diff against reality. If we head back to Azure, we currently don't have a subscription or a storage account created yet. Terraform is going to create 4 resources, so we can see in the plan 4 to add, 0 to change, and 0 to destroy. Let us go ahead and apply this by running the Terraform apply command. And we need to specify our subscription underscore ID again. Let's hit enter. Let us go ahead and say yes and hit enter. So now Terraform is actually communicating with Azure and provisioning our resources, the resource group, storage account, and the container. It will take a couple of minutes, so please be patient. And once the apply is completed, we should be able to see a new resource group created in Azure along with our storage account and the container. Terraform has successfully provisioned all of resources. It has created a resource group called rg-terraform-state. It has created a storage account which is globally unique along with a container name called tf state. If we head back to our Azure portal, we can see the resource group, and if I navigate inside the resource group, we have the storage account, and we should also have a container called tf state. Let us go ahead and check that. And this is where we're going to store all our Terraform tf state files for each environment. So it will be named as dev.terraform.tf state, UAT.terraform.tf state, and prod.terraform.tf state. And also one more thing I would like to highlight. On the left hand side, if you see, it has created the terraform.tf state. Currently, this stays on local. So if it is deleted, then your Terraform state will be lost. This workflow is perfect for local testing and bootstrapping. But in production environment, running Terraform from your laptop is a massive risk. It creates a single point of failure. Your laptop holds privileged access. Nobody else on your team can see the changes you are about to make. And your local state can easily get out of sync with reality. We are taking those local commands and automating them using the GitLab CI pipeline. Let's go ahead and create the .gitlab-ci.yml file in our Azure infra root directory. Let us select the directory, click on New File, and let's name our file as .gitlab-ci.yml. This is our GitLab-ci.yaml file. Let's break down exactly how this file makes our infrastructure secure, predictable, and fully automated. Look at the variable section at the top of our file. The most important thing here is what you don't see. There are no static Azure client secrets. Instead, we are setting ARM_use_OIDC to true. This pipeline uses workload identity federation. When a job runs, GitLab issues a short-lived ID token. Azure AD trusts this token and exchanges it for a temporary access. No secrets are stored in GitLab, meaning if your repository is ever compromised, there are no hard-coded keys for an attacker to steal. We have structured our pipeline into 4 distinct stages: validate, security, plan, and apply. First, validate ensures our code is properly formatted and systematically correct. It's cheap, fast, and fails early if we made a typo. Next is security. We are pulling in tfsec to run static analysis on our Terraform code. Before we ever attempt to touch our Azure environment, this stage scans our code to ensure we aren't doing something dangerous like exposing a storage account to a public internet. Next, we hit the plan stage. We're running this on every single merge request. Reviewers can look at the pull request and see exactly what infrastructure will be added, changed, or destroyed. But here is the most critical part of this entire pipeline. Notice how the plan job exports an artifact called tfplan, and the apply job explicitly consumes that exact same artifact. We never run Terraform apply blindly in automation. We apply the exact binary plan file that was generated and reviewed in the previous step. This guarantees zero drift. What you approve in the merge request is mathematically guaranteed to be what's get deployed. Finally, let's look at the apply stage. Automation is great, but we need guardrail. Notice the resource under group keyword attached to apply jobs. This acts as a concurrency lock. If 2 engineers merge code at exact same time, GitLab serializes the jobs. 2 pipelines will never race to apply against the same Terraform state file, preventing state corruption. And look at the apply:prod job. It is restricted to the default branch, set to manual, and tied to a GitLab protected environment. This means nobody can push straight to production. It requires a manual button click from a designated approver, like a platform lead, before Azure is touched. By moving from local CLI command to this GitLab CI file, we have eliminated hard-coded secrets, added automation security scanning, enforced peer reviews, and protected our state file. This is how we run Terraform in the real world. We have successfully built a fully automated GitLab CI pipeline to deploy our infrastructure. Let us go ahead and commit these changes to a remote repository. First, we need to replace our state_storage account name with the actual one. Let us head back to our Azure portal and let's copy the name of our storage account and replace it in the placeholder. Let us save and push these changes to remote repository. Let us run git status. So we have created the .gitlab-ci.yaml file. Let's go ahead and do a git add, and we specify the name of our file and hit enter. Let us rerun the git status again, and it is tracked. So let us do git commit -m added GitLab CI file. Let's hit enter, and we're going to push the changes to the remote repository by running git push -- set upstream origin main. Let's hit enter. Our changes are successfully push to a remote repository if I refresh the repo. But right now, our pipeline will fail. Why? Because GitLab doesn't have any keys to your Azure environment. And as we discussed, we refuse to generate static passwords or client secrets and paste them into our CI/CD pipeline. The process which I'm going to demonstrate next can be done manually, but we are going to run two bash script that bridges this gap. Inside the script directory, we have two scripts. The first establishes a secure passwordless handshake between GitLab and Azure. The second ensures that human engineers can actually log into the Kubernetes cluster once they are built. Let's break down what they do. Our first script is setup-azure-oidc.sh. These scripts automate the workload identity federation. When you run this, it creates an Azure app registration and grants it two crucial set of permissions. First, it grants contributor and user access administrator rights so Terraform can build out our network and cluster. Second, it explicitly grants storage blob data contributor to our Terraform state storage account. This is a crucial detail. Standard contributor access does not let you read and write data inside a blob. Terraform needs this specific data role to manage the state file. Finally, the script creates the federated credential. It basically tells Azure if you receive a token from GitLab and it specifically comes from our main branch or an active merge request, trust it. A quick note on architecture. For this demonstration, I'm running everything inside a single Azure subscription. But if you look at the top of the script, you will see variables for dev, UAT, prod, and shared. In a real enterprise organization, we'll map those to 4 completely separate Azure subscriptions to strictly enforce blast radius. Once the script finishes, it spits out exactly what variables you need to paste into your GitLab CI settings. Now that we understand what exactly this script does, let's go ahead and execute this locally and update the variables in Azure-infra GitLab repo. First, let us go ahead and update our storage account name. Let's head back to our Azure portal, copy the storage account name and replace it. Next, we need to update the subscription ID. If you head back to the portal again and click on the subscriptions, you can copy your subscription ID directly from here. I will select my subscription name and I will copy the subscription ID and I will replace the subscription ID for all our variables. Next, we have the GitLab issuer. In my case, I'm using gitlab.com. For organizations, you might have a different URL. You can just replace that with the actual URL. Next, we need to paste the GitLab project path. That would be your group, your subscription, or the name of the repository. Let's head over to gitlab.com. I will open the Azure Infra. And if I click on code and I will click on the HTTPS, so this will copy the URL. We're going to modify this. So our path is trailhead-supply-co/Azure Infra. Let's go ahead and paste that. And our branch is main. So rest of the things remains as it is. Let's go ahead and save this. I will open a terminal. I will navigate into the script directory. Before we can execute the script, if we head back to the Azure portal, go to the Azure Microsoft Entra ID, click on App Registrations and All Applications. And if I click on Created On, we currently don't have any app registration for our application, which is GitLab-AKS-platform. Let's go ahead and run the script. I will run /setup azure-oidc.sh. Let's hit enter. This will go ahead and check for an existing app registration, which is GitLab-AKS platform, which doesn't exist currently. Then it will go ahead and create that app registration and assign the roles. Let us give it a minute for it to do its magic. Once the script execution is completed, we will copy the variables and define it in our GitLab repo. The script execution completed successfully, and this is the summary. If we head back and refresh, we should have a new app registration called GitLab-AKS-platform. Next, let us go ahead and define these variables in our repo. First, I will copy the key, which is ARM_client_ID. Let's head back to our GitLab, click on Settings, navigate to CI/CD, then click on Variables. And under CI/CD variables, click on Add Variables. And we're going to specify the key name. Then we will copy the value and paste it. Let's click on add variable. Next, let us go ahead and define the ARM underscore tenant ID. Let us specify the key and add the value and click on add variable. And finally, let us define the ARM subscription ID. I'll just copy the key and I will copy the subscription and click on add variable. We currently using the same subscription ID for all our dev, UAT, prod and shared. So you can use the same variable, but in production, you generally scope it to the specific environments like dev, UAT, prod and shared. So our pipeline can now build clusters securely, but how do your developers and platform leads actually access those clusters to deploy applications or debug issues? We don't want to manage local Kubernetes accounts. We want to tie everything back to our centralized identity provider. That is what our second script, setup-AKS RBAC-group.sh does. This script creates two Azure Active Directory groups, AKS Platform Team and AKS Platform Leads. It then adds the email address of your team members into those groups. The script outputs the unique object ID of those groups, which we will paste directly into our Terraform variables. Our dev and UAT cluster will give admin access to the whole team, while our prod cluster will restrict admin access strictly to our leads group. Next, let us go ahead and create those two groups for team members and the leads. If we head over to the Azure UI and navigate to the Microsoft Entra and groups, we currently don't have any groups. Let's go ahead and execute this script. I will run /setup space AKS RBAC groups.sh. Let's hit enter. So this will go ahead and create the AKS platform team and AKS platform leads group. I have added myself as the user. So it has successfully created the groups and added the user. If we head back and refresh, we should have two new groups created. And we could see there are total two groups. One is called AKS Platform Leads. The other one is AKS Platform Team. Let me open the Platform Leads. And it has a single member. That is my name. So I have added myself as a member for both the groups. It's time to provision our shared environment using Terraform and GitLab CI. This will host our shared Azure Container Registry along with a AKS cluster where we're going to install Argocd and Kargo. Let's head back to our VS Code. Inside the environment directory, we have a subdirectory called shared. Let us open the terraform.tfvars where I'm going to update the subscription ID. Next, let us go ahead and update the tenant ID. I will head back to my Azure UI and I will copy the tenant ID and replace. And for the AAD underscore admin underscore group object ID, let us copy it directly from our output from the script. And I'm going to use the AKS admin principal ID. Let's go ahead and replace this. Next, we need to add the AKS admin principal IDs, which you can get that by simply running the az space ad signed-n-user show command. Let's copy that. Since we are already logged in using the az login command, let's go ahead and quickly run this command. So it will go ahead and output the value. Let's copy this and I will update the same. And if we scroll down, we have the networking, the log analytics workspace, then we have the AKS cluster, system node pool, and user node pool details. So those are the information. Let's go ahead and save. And let us go ahead and commit these changes, which will automatically trigger a pipeline in our repo, which will go ahead and provision our shared environment. Let us navigate into our Azure Infra repo by running cd space Azure-infra and let us run git status. So we have three changes, one for terraform.tfvars for shared directory, then we have the scripts modified. I'm going to only commit the changes for our terraform.tfvars for shared environment so that we can see how exactly our GitLab builds only the resources specific to that environment. Let us run git add and paste. Let us run git status again. So let us run git commit -m. We'll say provision the shared infra. Let's hit enter and run git push. And it is successfully pushed. If we head back to our GitLab repo, and in any seconds, we should have a new pipeline automatically triggered. And we have a new pipeline triggered 28 seconds ago. Let me open the pipeline and we can see we have 4 stages: validate, security, plan, and apply. and this is running against our shared environment, and it is not running against any of our other environments like dev, UAT, or prod. So the format is completed. So the validation stage is running now, and we have 2 green ticks. Now it is running the tfsec scan. Next, it is running the Terraform plan. Let us open the Terraform plan. So in the backend, the GitLab is spinning up a Docker executor on which it has the Terraform 1.15.8 installed. So it is going to run the Terraform plan. Once the plan is generated, then Terraform apply will use the plan and provision the infrastructure and Azure. And the job succeeded. It is going to create 18 resources and 0 to change and 0 to destroy. Let us go ahead and check the Terraform apply. Again, it is spinning up a Docker executor with the Terraform installed. If we head back to our Azure UI, we currently have the rg-terraform-state resource group in the central India. And once the Terraform apply is completed, we should have a new resource group along with our ACR and the AKS cluster. So it is running the Terraform apply against our TF plan. So it is provisioning the resource group. Now it is creating the AKS cluster. If we head back and refresh, we should have a new resource group called rg-acr-shared. If I open that, so it currently has the ACR, the Key Vault, and the log analytics workspace. It also created a network security group called nsg-aks shared. Provisioning the AKS cluster will take a couple of minutes, so be patient. The Terraform apply stage completed successfully. It has created 18 resources. Also, we have a couple of outputs. These values we are going to use in our other stages. Let's head over to our Azure Platform UI, and we could see that it has created ACR, AKS cluster along with Key Vault, and also a couple of other resources like log analytics workspace and NSG. Let's click on AKS shared. So this is our shared Kubernetes cluster where we are going to install Argocd and Kargo. So let's click on connect. We are going to use Azure CLI to connect to our Kubernetes cluster. We already logged in using az login command. Let's go ahead and download the cluster credentials using the az aks get credentials command. Before you can run that, ensure you have kubectl installed on your machine. Once done, let us go ahead and run the az aks get credentials command. Next, let us go ahead and use the kubelogin plugin for authentication, which is kubelogin space convert kubeconfig-l Azure CLI. Let's hit enter. It's done. Let us run kubectl get nodes to list all the nodes in our cluster. So we currently have 2 nodes, one called AKS-apps, the other one is AKS-system. Now let us go ahead and install Argocd on our shared AKS cluster. Let's head over to Argocd's official documentation. First, let us go ahead and create a namespace to host our Argocd by running the kubectl create namespace argocd command. Let's go ahead and install Argocd using the install.yaml file. I will copy the command, head back to my terminal, and execute. This will go ahead and install Argocd on our AKS shared cluster. Let's go ahead and monitor the status of our deployment by running kubectl get pods in the namespace Argocd, and we'll keep a watch. All our pods are in the running state. Next, let's go ahead and list all the services in the Argocd namespace by running kubectl get svc-n argocd. We are going to access the Argocd UI using the Argocd server. Currently, the service type is cluster IP. Let's go ahead and change this to load balancer. We can go ahead and use the following patch command, which will update our Argo server and change the service type to load balancer. Let me go ahead and execute that. And if we rerun the kubectl get svc in the namespace Argocd, we have our Argocd server type has load balancer and the IP is pending. Let us give it a minute, and once the load balancer is provisioned, we should have an IP address and we should be able to access our Argocd using the following IP. Let me copy that, head over to a browser, in a new tab, let's type http:// the load balancer IP and hit enter. So we currently don't have any valid certificates. click on Advanced, and let us click on Proceed to this IP. And this is our Argocd login page. We can log into the Argocd using the default username, which is admin. Let us get the password using the Argocd admin initial password command. In order to execute this, you need to have the Argocd CLI installed on your machine. This is our default password. Let's head back and let us go ahead and log in using the password. I will click on sign in. So we are successfully logged into our Argocd UI. The first thing I'm going to do is change the password. I'll click on update password, enter the current password, and I'll create a new password. So next time when we want to log in, we don't have to generate the default password. And we have successfully changed the password. Let us click on logout and log back in with our new password. And we have successfully logged in. Next, let us go ahead and install Argo Rollouts. I'm in the Argo Rollouts official web page. First, we'll create a namespace using kubectl create namespace command for our Argo Rollouts. Next, let us go ahead and install it using the install.yaml script. I will copy the command, head back, and execute that on my cluster. Let us go ahead and monitor the status of our deployment by running kubectl get pods -n argo-rollouts. And we'll keep a watch. And our Argo rollout pod is in the running state. Argo basic installation requires Kubernetes cluster with cert manager pre-installed. Argo rollout is optional. Argo's verification feature uses Argo rollouts analysis template and analysis run resource internally. We are using it in our project, hence we already installed Argo rollouts, but Kargo doesn't require your application deployment to use Argo rollouts. Let's go ahead and install cert manager. I will copy the following helm command, head back to my terminal, and execute. This will go ahead and create a namespace called cert manager and install the version 1.21.0. Let's go ahead and monitor the status of our deployment by running kubectl get pods in the namespace cert-manager, and we'll keep our. And all our pods are in the running state. Kargo has no default admin password or sign-in key. You must provide your own. We can generate them using the OpenSSL and HT password. First, let us go ahead and define a variable called pass. This will go ahead and generate a Kargo admin password. Ensure that you have OpenSSL installed on your machine. Let us go ahead and cat the content. So this is the Kargo admin password. Next, we need to generate the password hash. We will do that by running the following command, which will use HT password to generate the password hash. Next, let us go ahead and create a signing key using the OpenSSL. Now we can go ahead and echo both the values. So this is our password hash and the signing key. Save these somewhere safe like Azure Key Vault. You will need the hash and signing key for install and the plain text password to log in. Kargo charts are hosted as an OCI artifact on ghcr.io, so there is no traditional Helm repo add. You pull it directly by reference. Extract the default values file first so we can edit only what we needed. Before we can go ahead and pull that, ensure you authenticated to GHCR using the Helm registry login command. Let's go ahead and run helm show values command and save the default values to cargo-values.yaml file. Let's hit enter, and the values.yaml is successfully pulled. Let us edit the cargo values.yaml file. I will run vim cargo-values.yaml. Let's hit enter. First, let us go ahead and update the admin account's password hash. I will search for password hash. Let us go ahead and update the password hash. Next, let's update the signing key. Let's go ahead and save and exit. Now, let's install Kargo using the helm install command. I will run helm install and I will call my release as Kargo, and the version is 1.10.9. We're going to create a namespace called Kargo since it does not exist, and we'll pass our values.yaml file. Let's hit enter. So this will go ahead and install Kargo on our shared AKS cluster. Let's go ahead and monitor the status of our deployment by running kubectl get pods in the namespace Kargo, and we will keep a watch. Once all our pods are in the running state, you should see a Kargo API, Kargo controller, and Kargo webhook server running. Next, let us go ahead and run kubectl get svc to list all our services. And we should be able to access our Kargo UI using the Kargo API service. Currently, the Kargo API service type is cluster IP. Let us go ahead and update the type to load balancer. I will run kubectl edit svc cargo-api in the namespace cargo. Let us go ahead and change the type from cluster IP to load balancer. Let's save and exit. And our service is edited successfully. Let us run kubectl get svc-n cargo again. And the service type is changed to load balancer and the external IP is pending. Let us give it a minute. So we have an external IP. We should be able to access the Kargo UI by hitting the following external IP address. I will copy the IP, head over to a browser, and in the new tab, I will type http:// and the load balancer IP. Let's hit enter. Let us go ahead and log in using the default admin password and click on login. Now we have a fully automated secure Azure Kubernetes service running, but an empty cluster doesn't serve customers. Today, we are bridging the gap. We are going to deploy our microservices using highly secure GitLab CI pipeline and GitOps workflow. If you look at our repository, it is a monorepo containing 4 distinct microservices: UI, catalog, recommendation, and review. We need a pipeline that is smart enough to only build what changed and secure enough to guarantee that a vulnerable image never reach our Azure Container Registry. Let us go ahead and create a GitLab CI file in the root of our app service directory. Let us click on app services, create a new file, and type .gitlab-ci.yml. This is our full pipeline, 5 stages, and I want to walk through each one properly because pipeline file is easy to skim past, and this one has a couple of decisions in it that are the actual point, not just boilerplate. Test run first, and it's exactly what you would expect. One job per service in that service own native toolchain. npm or node check for the UI, pytest adjacent check for the catalog service, go wet and go build for recommendations, maven test for reviews. Nothing exotic, fast, cheap source level checks, and worth nothing. Every one of these jobs is scoped with a rule and a change block. So change to only the catalog service doesn't waste time retesting the other 3. Build is where the first real decision shows up. Look closely at this Kaneko invocation. -- no push paired with -- star path. This builds the image, tags it. Notice it gets tagged twice, once with a semantic version and once with the raw commit SHA for human traceability. But instead of pushing either tag anywhere, it writes the whole thing out as a local file. That tarball becomes a GitLab artifact handed to the next stage. Security scan is the reason for that choice. Privy scans the tar file directly, reads from a local file, not pulling from a registry, which means this scan needs 0 registry credentials, and more importantly, it means the image was never lived in our container registry while it was still unscanned. If Trivy finds a high or critical vulnerability here, the -- code is set to 1, which fails the job, the pipeline stops, and that image simply never reached the next stage. Not reverted, it never existed anywhere but this one's local runner's disk. Push, which only runs if the scan passed, take that exact same tarball, not a rebuild, the identical bytes that were already scanned, and pushes it to the Azure Container Registry with Scopio. And update _GitOps _dev, the last stage, is what actually connects this repository to environment-config-gitops repo, which we are going to create in this video later. That said line is a small, deliberate piece of defensive engineering. It strips whatever schema the GitOps _repo _URL variable happens to be set with, whether that's HTTPS, RNSSH style git at host prefix, before rebuilding it as a token authenticated HTTPS URL. It's the kind of one-line fix that only exists because a real specific failure happened once and got solved properly instead of workaround. And the YQ line right after it is the entire mechanism that makes this whole platform's promotion story work. one YAML key in one file in a different repository entirely, updated automatically with a commit message that traces every single change back to the exact source commit that caused it. That commit is where this pipeline job ends. It never touches Kubernetes. It never runs kubectl or Helm. It updates one line in Git and stops. Because from that point forward, it's Argocd's job, not its pipelines. Notice that commit and make devs cluster match it. We'll watch that actually happen live later in the video. Alright, so our application pipeline is fully defined. It knows how to build, scan, and push. But right now, it is completely locked out of both our Azure Container Registry and our GitOps environment. To bring this pipeline to life, we need to inject 4 specific CI/CD variables into GitLab. We are going to set this up in Settings, CI/CD, and Variables section, and we are going to ensure they are masked. Let's walk through exactly where to get these values. Our first variable is ACR_login_server. This one is easy. If you remember from our infrastructure deployment, we created a shared environment using Terraform. Go look at the output from the Terraform apply job. You will find your ACR login server URL right there. It usually looks something like your registry name followed by .azureecr.io. Grab that and paste it in. Let's go ahead and do that. I will copy the variable name. Let's head back and we'll head back to our app service repo on GitLab. Let's click on settings and navigate to CI/CD, and we'll go to variables and define our variable and add CI/CD variable. And let's add the key, which is ACR login server. Let's go ahead and copy the value and paste. Let's click on add variable. So we have successfully added our first variable, which is ACR_login_server. Now for the most important variable, ACR_docker_auth_config. A lot of tutorials will tell you to just go into the Azure portal, click enable admin user on your registry, and paste those credentials into GitLab. Do not do that. The admin account has all or nothing access to every single repository in your registry. If that credential leaks, your entire registry is compromised. Instead, we practice this privilege. Let's open a terminal, and I will walk you through exactly how to build this securely command by command. Let us define a variable called ACR_name and set it to the actual value. Then we use the following Azure CLI command to create an ACR scope map. We run this command to explicitly tell Azure only grant push, pull, and read metadata access strictly to our 4 microservice repositories. Let's go ahead and hit enter. Next, we run the ACR token create command. This generates a token securely bound only to the scope map we just created. Azure will output 2 passwords for rotation purpose. Copy the value of password 1. Let's go ahead and do that. Now we need to format this for GitLab. You don't need Docker installed locally to do this. We just run a simple printf command in the terminal to combine our token name and password, and then pipe that into a standard docker config.json file format. Let's go ahead and do that. First, we're going to define variable called auth. Next, we're going to generate the docker config.json file using the following cat command. And it has generated the docker-config.json file. Finally, we take this config.json and base64 encode it. Let's go ahead and do that by running the base64 space -wo, then the name of the file, which is docker-config.json. That base64 string right there, that is what you copy and paste it into GitLab as your ACR docker auth config. Let's go ahead and do that. First, I'm going to copy the variable name. Let's head back and we'll add the key, and we will copy the value, the base64 encoded value, and we will define that and click on add variable. Make sure you check the masked box so it never shows up in your CI/CD logs. And a quick pro tip, delete that docker-json.config file off your laptop the second you are done. It is a live credential and you don't want it to sitting on your local drive. Our final 2 variables handle GitOps handoff we discussed earlier. The pipeline needs to know where to commit the new image tags, so we define GitOps underscore repo underscore URL. This will point to our environment config GitOps repository, which we are actually going to create now. Let's head back to our gitlab.com, and in a new tab, let us navigate to TrailHead Supply Co group and click on Create Project. I'm going to create a blank project, and we're going to name this env-config-gitops, and we will leave the visibility level to private, and we'll click on Create Project. And our project is successfully created. Let's go ahead and copy the HTTPS URL, head back, and we are going to create a new variable with this value, and the variable name is GitOps underscore repo underscore URL. Let's go ahead and add that in the key. There is a space, let's remove that, and we're going to click on Add Variable. Finally, our pipeline needs permission to push those new tags over to our GitOps repository. This is where GitOps underscore repo underscore token comes in. In a paid enterprise environment, you would create a tightly scoped project access token for this. But here is a crucial gotcha if you are following along on a GitLab free tier account like me. Free tiers do not support project or group scoped access tokens. To make this work, we have to create a personal access token at the account level instead. Let's click on our profile icon and select Preferences, and go to Access and select Personal Access Token. We're going to generate a token using the legacy token method, and I'm going to name my token as app-service-ci. For scope, we are going to practice this privilege again, check the right repository, and nothing else. The pipeline does not need full API access, it just needs to commit code. You can set the expiration to 90 days is a standard strict practice. So we'll go ahead and set it to October 2026. Then click on Generate Token and copy the token immediately because GitLab will only show it to you this one time. Head back over to your app service repository one last time and save that value as your GitOps underscore repo underscore token variable. Let's head back and do that. The CI/CD, let us go ahead and copy the GitOps underscore repo underscore token, and I will update the key. Let us remove space again. And one last time, let us go ahead and copy the token, and we'll add the value, and we'll click on Add Variable. With those 4 variables saved, our application pipeline is officially armed and ready. We have secure, tightly scoped access to Azure and programmatic access to our configuration state. Now it's time for the moment of truth. We are going to trigger this pipeline and watch it build, scan, and push our microservices completely automatically. Before we kick this off, let's verify our starting state. If we jump over to the Azure portal and look at our container registry, you can see this repository list is completely empty. We have 0 images. To trigger the pipeline, we need to introduce a change. In our code editor, inside our 4 microservices directory, there is a simple version file. I'm going to bump the version tag in every single one of them. Next, I'm going to comment the update underscore GitOps underscore dev stage because the repository is completely now. We stage those version bumps along with our brand new .gitlab-ci.yaml file using the git add command. Let us run git status. So we have 5 changes, the version bump for our services and our GitLab CI file. Let's go ahead and do a git add dot. Let us verify by running the git status again. Let's go ahead and commit those changes. I will run git commit -m build and push images to ACR. Let's go ahead and push. I will run git push -- set upstream origin main. Let's head over to our GitLab. The pipeline instantly pick up the push. Look at this graph. Because we bumped the version in all 4 services, GitLab dynamically spins up parallel jobs for every single one of them. First, our unit test run. Next, Honeyco steps in. It builds the container image and outputs them as local tarball exactly like we designed. Then Trivy takes over. It scans those local tarball for vulnerabilities. Since our code is clean, the security gate pass, Scopio picks up the artifacts and push them securely over to Azure. So our pipeline execution is completed successfully. If we head back to Azure and if I refresh the repository, we currently have 4 images for catalog, recommendation, review, and UI service. Let me select the catalog service, and we have image with 2 tags. One is the SHA commit for our reference, other one is 1.2.2. Our custom microservices images are safely stored in our Azure Container Registry, but if we deploy right now, our application will fail. We are missing the critical component, our database. Our application relies on PostgreSQL, but unlike our UI or catalog service, we aren't writing a custom Docker file to build a database from scratch. We need to use the official image. You might be wondering, why don't you just configure our Kubernetes cluster to pull Postgres directly from our Docker hub? In production environment, relying directly on a public registry is a massive risk. You can hit anonymous pull rate limits, experience upstream outages, or fall victim to a bad updated overwriting attack. Instead, we are going to pull the official image down our local machine, retag it, and push it to our private secure Azure Container Registry alongside our 4 custom services. This ensures our AKS cluster only pulls from an internal trusted source that we fully control. First, we need to authenticate our local Docker daemon with our Azure registry. Let us run AZ-ACR login -- name of our container registry, and we are logged in successfully. Next, we'll pull the official image using the docker pull command. I will run docker pull Postgres, and we're going to pin the version to 16-alpine. Let's hit enter. Once the image downloads, we run the docker tag command. We take that downloaded Postgres image and attach our ACR login server URL to the front of it. This tells Docker exactly where this image belongs. Finally, we execute docker push with that new tagged image, and the image downloaded successfully. Let us tag our Postgres image using the docker tag command, followed by the container name .azureecr.io/postgres:16 alpine. Let's hit enter. I will copy the image name. Let us run docker push followed by name of our image, and let's hit enter. All right, our image is successfully pushed. If you refresh your Azure portal, you will see a 5th repository sitting next to our microservices. Our private registry now holds everything our cluster needs to run the entire application stack. The env-config-gitops repository is the single source of truth for how our applications are configured, deployed, and promoted across our Azure Kubernetes Service environments like Dev, UAT, and Prod. It picks up right where our application code repository app services leaves off. Once the CI pipeline builds and pushes a new container image tag to Azure Container Registry, this GitOps repository takes over to manage deployment and environment promotions using Argocd and Kargo. The repository is structured into 3 main top-level directories. First, charts. This directory contains our shared Helm charts definition for all our microservices, including the UI service, catalog service, recommendation service, review service, and review DB. It also houses the TrailHead-platform umbrella chart, as well as a dedicated platform secrets chart for external secret operator configuration. Second, environments. Here we separate configuration for dev, prod, and UAT. Each environment folder contains app/values.yaml file, which stores the active image tags and application settings. The platform houses the Argocd application manifest, cargo stage definitions, analysis templates, and observability alert tailored to that environment. Third, we have the platform repository. This contains the global GitOps definition shared across all environments, such as Argocd app project and root app of apps manifest, and Kargo's warehouse polling policy. We manage deployment scaling using Argocd's app of app patterns. There is a single root application manifest located at platform/argocd/root-app.yaml. This is the only manifest applied manually during initial setup. Once deployed, the root application continuously monitors the environment /dev, UAT, or prod/platform and automatically discovers, deploys, and manages all child applications. Currently, It manages child applications for dev, UAT, and prod, along with platform secret manifests. Adding a new environment in the future is as simple as adding a new environment subfolder. Argocd picks it up automatically on its next sync. We just walked through the directory structure of our env-config-github repository. Now it is time to initialize it as a Git repository and push it up to GitLab. But before we run Git init, we have to establish our baseline configuration. Right now, our GitOps repo is essentially a template. We need to wire it up to the private Azure Container Registry we just populated. First, we need to configure our base Helm charts. Navigate into the charts directory. For every single microservice, like UI, catalog, recommendation, and review, you need to open the values.yaml file, find the image.repository field, and update it to point directly to your specific ACR login server URL. While you are in there, update the image.tag to match exact version tag we just built a couple of minutes ago in this video. Don't forget to do this for Postgres database chart as well, pointing it to the official image we manually tagged and push to our private registry. I went ahead and updated the image.repository and the tag for all my services. With our configuration logged in, let us go ahead and open our terminal, and at the root of our directory, let us go ahead and initialize this as Git repository. I will run the following git init command. Next, let us go ahead and do a git remote add command. Next, let us run git status. Let's go ahead and do a git add and run git commit -m. I will say initial commit. Let's hit enter and run git push -- set upstream origin main and hit enter. So all our changes are pushed to the remote repository. If we head back and refresh the page, we should have our configuration file pushed to our GitLab repo. Let us deploy our TrailHead application to dev environment. Behind the scene, I went ahead and let our Terraform pipeline provision our dev environment. To make that happen, I updated the terraform.tfr file for the dev environment. The configuration is standard, like the subscription ID, the tenant ID, the group object ID, and the admin principal ID. But there is one crucial new value required for dev, UAT, and prod. That is the ACR ID. We simply grab this ID from the Terraform apply output of our shared environment and paste it in it. With the cluster up and running, let's connect our local terminal to it using the AKS get credentials command. Let's head over to our Azure dashboard, select our dev resource group, and let us select AKS dev cluster. I'll click on connect, and we will use the Azure CLI. We already logged in using AZ login. Let's go ahead and download the cluster credentials again. I will head over to my terminal and I will execute. Next, let us go ahead and use the kube login plugin for authentication. Let us copy this and let us go ahead and run the command. If I run kubectl get nodes, we should have the nodes for our dev cluster, which are in the ready state. Now it's time to deploy our application using Argocd. Let's open the values.yaml file under environments, dev, and apps in the env-config GitOps repo. This file is the brain of our dev deployment. It overrides our base Helm charts with environment-specific configurations. Look at the replica count, the resource limit, the database credentials, and the internal service URLs. If an engineer wants to scale up a service or change a memory limit, they do not run kubectl commands. They open a pull request against this exact file. But notice the image.tag field. This is the magic of the pipeline we built earlier. The image tag is the only field in this entire file that changes automatically. Every time our GitLab CI pipeline successfully builds a new image, the update_GitOps_dev job programmatically commits the new version right here. Now we need to tell Argocd where to look. Let's update our Argocd manifest. First, open environment/dev/platform argocd application.yaml. You need to update the source repository URL to point to your GitOps repository. In our case, it is env-config-gitops. And we need to set the destination server URL, which we can get from our kubectl command. Let us head back to our terminal. If I currently run kubectl config get contexts, we have two clusters, one for AKS shared, the other one is AKS-dev, and the current context is set to AKS dev. So let us run kubectl config space view, then go ahead and specify the following JSON path, which will print out the cluster details. Let us go ahead and copy this and update our destination server URL. Next, we are using the app of app patterns. So we need to configure our root application. Open Platform, Argocd, and root-app.yaml. Here, update the source repo URL. I simply went to our GitLab, then copied the env-config-gitops HTTPS URL, and I updated the repo URL. But pay close attention to the destination server here. This needs to point to the shared AKS cluster because that is where Argocd itself is hosted. Let's head back to our terminal. Let's go ahead and set our current context to AKS shared by running kubectl config use context, and we're going to say AKS shared. Next, let us go ahead and run the kubectl config view command to get the server URL. This is the server URL for our shared environment. Let's go ahead and copy this, and we'll update the destination server. Finally, open the project.yaml file. Argocd uses projects to restrict where application can be deployed. We need to update the destination.server list. Let us go ahead and do that. For the namespace Argocd, we will add the shared cluster server details. Next, let us go ahead and add the dev cluster URL. I will head back to my terminal and I will copy the dev cluster server URL and I will update. So this will whitelist both our Argocd shared cluster and our target dev cluster. There is one last piece to this puzzle. Our env-config-github repository is private. Argocd is going to get a permission denied error if it tries to clone it right now. Open the repo-credentials.yaml file. This manifest creates a Kubernetes secret that passes authentication details to Argocd. I have already created a personal access token called Argo-service-ci because Argocd only pull configuration and never pushes. We strictly scope this to have read-only permission. Copy the token and drop this into this file, which I already did, and Argocd will finally have the key to read your repository. Our GitOps repository is fully configured. Our destination clusters are defined and authentication is securely handled. The stage is set. Let's apply this manifest to the cluster and watch Argocd synchronize our entire microservice architecture in real time. I've already logged into my Argocd instance and we currently have no applications. And if I navigate to settings and click on repository, we currently don't have any repositories. First, let's go ahead and apply our project.yaml file. I will open a terminal. I will run kubectl apply -f platform/argocd/project.yaml. This will go ahead and create a project called TrailHead. Next, let us go ahead and apply our repo-credential.yaml. I will run kubectl apply -f platform/argocd, then repo credentials.yaml. Let's hit enter. So this will go ahead and create the credentials. If we head back to our Argocd UI and refresh the list, we should have a new repository which is connected and successful. Before you go ahead and push these changes to a remote repository, make sure that you go ahead and delete the following password or include this file in the .gitignore, so this will not be committed to the remote repository. So I will go ahead and remove this password. Before we apply the root-app.yaml, let's go ahead and push our changes to the remote repository. I will run git status, and we have the following files updated. Let us go ahead and do git add, then do a git commit, and let us do a git push. And our changes are successfully pushed to a remote repository. Let's head back, and if I refresh the env-config GitOps repo, we have a new commit which is 30 seconds ago, and we have our new changes pushed. Next, let us go ahead and register our clusters using the Argocd cluster add command. Let us go ahead and run the kubectl config get context command. So we have the context, AKS dev and AKS shared. I already logged into Argo CD using the Argo CD login followed by the load balancer IP. Next, I'm going to run Argo CD cluster list, and we currently have the default cluster, which is the in cluster. Let's go ahead and run Argo CD cluster add. Then first we're going to add the AKS shared cluster. Let me enter. I'm going to say yes. So it is successfully added. If I rerun the Argo CD cluster list again, so we have two cluster now. One is in cluster, the other one is AKS shared. Let us go ahead and add our AKS dev cluster. I will run Argo CD cluster add AKS space dev. Let's hit enter. I will go ahead and say yes. And our AKS dev cluster is also added. Let's run the Argo CD cluster list command for one last time. And we should see our two clusters, AKS shared and AKS dev added. Next, let us go ahead and apply our root app.yaml. If we head back to Argo CD and click on applications, we don't have any applications. Let us go ahead and do that by running kubectl apply -f platform argo cd root-app.yaml. Let's hit enter. And if we head back to our Argo CD, we should have a new app coming up in any seconds. All right, there you go. We have our root app called TrailHead-root. It basically spun up our application for our dev, UAT, and prod. And currently, we don't have any server or URLs defined for prod and UAT, so they should not be healthy. But if we take a look at the dev cluster, it is in the progressing state. And this is our TrailHead Co application, which is being deployed to our dev AKS cluster. And we have the following resources, like we have secrets, services, deployments. And currently, the deployment is in progress. And we could see we don't have any errors so far. And it will take a couple of minutes before everything is turned to green. Once our application is successfully deployed, we will head back to our CLI and we'll verify if everything is deployed as intended. Let's switch our context. If I run kubectl get namespaces, we should have a new namespace called TrailHead-dev. Let us run kubectl get pods-n and we'll keep a watch. So our TrailHead dev catalog service, the recommendation service is running. Now the UI service is running. The DB service is also running. So we are waiting for the review service to be up. Okay, our review service is also running. Let me cancel. If we rerun the kubectl get pods command again, and we should have all our 5 services up and running. So let us run the kubectl get svc in the namespace TrailHead-dev. So we have our services. If the dev UI service is a type of cluster IP, we can go ahead and use a port forward to quickly test if our application is working as expected. Let us run kubectl port forward the service TrailHead-dev UI service in the namespace TrailHead-dev, and we will port forward it to 3000:3000. Let's hit enter. Okay, let's head back to our browser, and in a new tab, I will open localhost port 3000. And our application is working as expected. So if I click on the product, we are able to the product and we see the reviews for the product. Our TrailHead Supply Co e-commerce platform is running smoothly in our dev environment via Argo CD. Behind the scene, I went ahead and used our Terraform workflow to provision our UAT and prod cluster, and I have onboarded both of them into Argo CD and updated Argo CD project.yaml with their server URL. But before we deploy our application to this higher environment, we have a massive security flaw to fix. In our dev environment, our PostgreSQL database password is just sitting as plain text inside our Git repository. For local testing or a disposable dev cluster, you can get away with that. For UAT and production, that is critical security violation. Today, we are stripping all hard-coded secret out of Git and moving them into Azure Key Vault using the external secret operator. Before we type any commands, let's quickly look how this works. Normally, when a pod needs a password, it reads a native Kubernetes secret, but we don't want to manually create those secrets, and we certainly don't want to store them in Git. Enter the external secret operator, or ESO. ESO runs inside your cluster and acts as a bridge. Using Azure Workload Identity, ESO securely authenticate with Azure Key Vault without needing any password itself. It fetches the real database password from the vault and then dynamically creates a native Kubernetes secret inside your cluster. The beauty of this architecture is that your application pod don't need any special SDKs or code changes. They just consume standard Kubernetes secrets exactly like they did before. They have no idea ESO is even running. We understand the theory behind the external secret operator and workload identity now. Let's actually build it. Open up your terminal. We are going to execute this setup for our UAT cluster, but you will follow these exact same steps for production. Ensure you have set your context to AKS UAT. You can use the kubectl config use context command. Next, go ahead and define the following two variables. First, the resource group and the cluster name. You can get that directly from your Azure dashboard or your Terraform output. Let's hit enter. Run this AKS update command on your existing UAT cluster. We are passing --enable -OIDC -issuer and --enable -workload -identity. Once the cluster updates, we need to extract the specific OIDC issuer URL that Azure assigned to it. Once the cluster updates, we need to extract the specific OIDC issuer URL that Azure assigned to it. We can run the following command, and this is our AKS OIDC issuer URL. Run the AKS show command and query for the issuer URL. Copy that output and keep it handy. Azure Active Directory need this URL to trust our cluster. Next, let us get the operator running inside our Kubernetes cluster. We add the external secret Helm repository using the Helm repo add command and run a simple Helm upgrade command --install to deploy it in its own dedicated namespace. And our external secret operator Helm charts are installed. We can run the kubectl get pods in the namespace external secrets to verify the operator is running successfully. Currently, the operators are in the container creating state. Let us go ahead and keep a watch, and we see all our pods are in the running state. Now, for the most critical part, writing the identity. Let's go ahead and create a variable called environment, and we'll set it to UAT. First, we create the Azure managed identity. Let's call it TrailHead-ESO-UAT. Let's go ahead and hit enter. We then run two quick queries to extract the client ID and principal ID. First, I will run the following command. We'll extract the client ID. Next, let us go ahead and run the following AZ identity show command, which will extract the principal ID. We can go ahead and echo both the values by running echo. This is our client ID and this is our principal ID. Next, we create the federated identity credential. This command is where a lot of people make mistake, so pay attention to this --subject line. The subject must perfectly match the Kubernetes namespace and service account name that our application will use. In our case, the namespace is TrailHead-UAT and the service account is TrailHead-ESO-UAT. If there is a typo here, Azure will silently block access. We run the federated credential create command and then verify it with a list of commands to ensure the subject is mapped correctly. Let's go ahead and execute this AZ identity federated -credential create command. So it is executed successfully. Let's verify it with a list command to ensure the subject is mapped correctly. I will execute the AZ identity federated -credential list command. Our identity exists, but it does not have permission to read anything yet. We use Azure RBAC to grant our managed identity the Key Vault secret user role, scoped specifically to our TrailHead Key Vault. First, let us go ahead and create a variable called Key Vault _name, and we will set it to our Key Vault in UAT. We can head back to our Azure dashboard and copy the name of our Key Vault. Next, let us define the vault ID. I will run the following AZ Key Vault show command followed by the name of our Key Vault. We will query the ID. Next, let us go ahead and use the AZ role assignment create command to assign the role Key Vault secret user to our vault. Let me go ahead and hit enter. And we can go ahead and verify the role assignment by running the az role assignment command. Let's hit enter, and the role assignment is done successfully, and it is currently the Key Vault secret user role. Now let's give it a secret to fetch. We use OpenSSL locally to go ahead and generate a random 24-character password and temporarily write it to our text file. Let me go ahead and hit enter. Next, we'll push that file directly into Azure Key Vault using the az Key Vault secret set command, naming it as review-db-uat-postgres-password. So we got an error message stating that caller is not authorized to perform the action on this resource. This is happening because Azure CLI is using our logged in account instead of AKS workload identity. Let us go ahead and grant ourselves Key Vault secret officer role. First, let us get the object ID by running the az-ad signed in user show query. Now let us list the assignment by running the az role assignment list command. We see nothing, that's the problem. Let's go ahead and grant ourselves Key Vault secret officer role, which is sufficient for us to push our secret to the vault. I will run the following az role assignment command. This will go ahead and grant a Key Vault secret officer role to our object ID, and it is executed successfully. Wait a minute or two for RBAC propagation, then retry again. Let me run the az Key Vault secret set command again. So if we head back to our Key Vault and refresh, we have a new secret called review-db-uat postgres password. Immediately run the rm to delete the local text file. The only place that password exists now is securely inside Azure. The cloud infrastructure is done. Finally, we tell Argocd how to deploy our app using these new tools. In our GitOps configuration repository, we update our UAT values.yaml file. We instruct Helm to create our service account and attach our Azure client ID. Let us get the Azure client ID by echoing the client ID. Let me copy this, head back, and we'll update the client ID and save. We define our secret store pointing to our Key Vault URL. We can get the Key Vault URL from our Azure dashboard. I will head over to our UAT resource group, which is rg-AKS UAT. Then there is a vault URL. Let me copy that and update our values.yaml file. And we define the external secret resource, telling it exactly which remote key to fetch and how often to poll for rotation. Before proceeding further, go ahead and repeat the exact steps we performed a couple of minutes ago and update the values.yaml for your production environment with the service account client ID, the vault URL, and the external secret remote reference. I went ahead and did that, and this is our production Key Vault, and I have pushed the review-db prod postgres password. And if I click on overview, see the resource group name is rg-AKS-prod. So one last minor change before go ahead and commit these changes and push them to GitLab. Let's go ahead and reapply our platform Argocd project.yaml file because we have updated the server details for UAT and production. Let's open a terminal. Make sure that you are switching your context to AKS shared environment. Once done, let us run kubectl apply-f platform/argocd/project.yaml. Let's enter. So our project is configured. Now let us run the git status command, and we have modified our platform values.yaml for prod and UAT. Also, we have updated the server details for our Argocd project.yaml file. Let's go ahead and commit these changes. I will run git add, then run git commit. Then we're going to save updated UAT and prod config files. Done. Let us go ahead and run git push, hit enter. Our changes are successfully pushed to our remote repository. We head over to our GitLab, the env GitOps repo. We have our new commit message. Let us navigate to our Argocd UI, and we could see our TrailHead root application is synced, but none of the applications related to UAT and the prods are up. Let us select the UAT application, and we have an error message. Let us check. So it says that destination server missing app spec. Let us check the application for prod and what exactly the prod environment. Select same, and we have the same destination server missing from the app spec error. So let's head back to our VS Code. I will minimize this. So let us navigate to UAT. First, we'll check the Argocd application.yaml. Let us scroll down. So we missed to update the server details in our Argocd application.yaml. So let us go ahead and copy UAT server details from our project.yaml. I will navigate to argocd-application.yaml for our UAT, and I will update. Let's do the same thing for our prod environment also. Let's copy server details. Let's open the prod application.yaml file and update the server. Okay, go ahead and save. Run git status again. So we have changes for our Argo application for prod and UAT. Let us run git add and commit these changes. Updated UAT prod Argo apps. Put in changes by running the push, and our changes are successfully pushed. Head back to our Argo CD and let us go ahead and open pilot root application. I will go ahead and forcibly sync. I will click on synchronize so that it can pick up the changes. All our applications are healthy and synced. That's good news. Let's head back to our terminal and try to get the secret store by running the kubectl get secret store in the namespace TrailHead-prod. It should say ready. That is true in our case. Next, let us try to get the external secret store in the namespace TrailHead prod environment. It also says that it's ready and the secret is synced. Finally, let's look at the actual native Kubernetes secret that ESO generated for us. Run this command to extract the Postgres password payload and base64 decode it. If you see your generated password printed on the screen, your pipeline is complete. Keyword pass the secret to the operator. The operator built the Kubernetes secret and your pods are ready to securely consume it. You are officially ready for production. Let's make an actual change and watch it flow through the whole system. I'm going to make a small visible change to the catalog service just so it's obvious on screen when it's landed. So we have a product called Contour 45-liter backpack, and it also have a description of 45 in it. Let's go ahead and change it to 55. I'll click on services, navigate to catalog services. Under app, we have data.py. So under product, we have the Contour 45 backpack. Change it to 5. And also in the description, let us change from 45 to 55. Let's save and go ahead and commit these changes to a remote repository. Let us run git status. And if you remember, we head back to the GitLab.ci YAML file. We have commented out the update GitOps dev repo because we not had any configuration in our GitOps repository. I went ahead and uncommented the stage update GitOps dev. And if I scroll down, so this is the stage which I commented previously. So I uncommented all the stages. Let's go ahead and push these changes. Let's run git add. And let us go ahead and say commit -m the catalog refresh product copy. Let's go ahead and push changes to a remote repository by running git push -- upstream origin main. Just want to point out one thing. In practice, you generally don't push directly to main because main will be a protected branch, and developers usually create their own feature branch and they will go ahead and create a pull request which will be reviewed by a senior developer. Once the pull request is approved, then they can go ahead and merge it to the main. Just to keep it simple, I'm just pushing the changes directly into the main repository, but this is not the way you're going to work in an enterprise. Let's go ahead and hit enter. Our changes are pushed repository, and if I refresh the app service repo, you see a new pipeline off. Let us open the pipeline. It only triggered the pipeline related to the catalog service, so it has run the test. Now it is running the build stage, where Kaneko builds the catalog service image, and it go ahead and create a tarball and uploads the artifact. Next, we have the security scan stage. This is Trivi scanning the local tarball for known CVEs. No network pull needed since it's scanning a file sitting right here on the runner. Severity threshold set to high and critical. Either shows up, this job fails, the pipeline stops, and this is the whole point. That image never reached our registry at all, not reverted, never existed there in the first place. But we have a couple of high and critical vulnerabilities. Hence, I have set it to 0, so our pipeline is passing. Next, let us go ahead and check the push stage. The exact same tarball we already built and already scanned, not rebuilt. The identical bytes get pushed to Azure Container Registry tagged with a semantic version. And the last stage is the one that actually connects our app service to our env-config GitOps. This job clones our GitOps repo, finds the environment/dev/apps values.yaml file, and bumps exactly one line catalog service image tag and commits that straight into main. Let's head over to our env-config GitOps repo. Look at that commit. One line changed, made by CI, not by a person, with a clear commit message trying it back to the exact source commit that caused it. That's traceability. 6 months from now, if something wrong in dev, that is a paper trail, not a guess. Let's switch over to our Argocd. And because Argocd is always watching this repo, remember, pull based, not push based, it noticed that commit within seconds and it already syncing. Let us go ahead and head over to a terminal. I run kubectl get nodes. We're currently using the AKS dev cluster. Let's run the kubectl rollout status, and our changes are successfully rolled out. And we could see that we have the commit, which is dev bumped catalog service to 1.2.3. So that is the commit made by our GitLab CI, not by any human. So let us go ahead and port forward our service and see if the changes are automatically deployed into our dev environment. I will run the kubectl port forward command. Let us head back to our terminal. In a new tab, I will open localhost 3000. Our e-commerce platform is up and running, and we could see our contour 45 liter is changed to 55 liter backpack, and also see 5 liter top loader. And there our changes live in dev, from git push to running pod, 0 manual deployment steps, a full security scan in the middle, and a complete audit trail. Dev's the easy part. Though dev is supposed to move fast, the real question is, how does this same change get to UAT, eventually to prod, without just automatically doing the same thing everywhere, which would defeat the entire point of having separate environments. That's Kargo's job. Let's go watch it work. Quick mental model before we actually implement it in our environment. Kargo has 3 core concepts, and once this clicks, everything else makes sense. A warehouse watches your artifact sources. For us, that's our 4 container image repositories, ACR. Every time it sees a new version shows up, it bundles the current state of everything it's watching into a freight. A single named immutable snapshot, these exact image version together right now. And a stage is one step in your pipeline, dev UAT prod, that can request freight, verify it's healthy, and either auto-promote it forward or wait for a human. Now that we have covered the high-level architecture of Kargo's core components, projects, warehouse, and stages, let's dive into how these are declaratively configured inside our env-config GitOps repository. All platform-wide Kargo configuration resides under platform/Kargo. Let's walk through these 5 core files step by step in our setup. First up is project.yaml. This file instantiates a Kargo project named TrailHead. Think of a Kargo project as a top-level logical boundary and multi-tenant container. It binds our warehouse, stages, and secrets under a dedicated Kubernetes namespace where all automated promotion workflows execute. Next, we have GitLab-repo-creds.yaml. This Kubernetes secret is labeled with cargo.akuti.io/cred-type::git. It provides Kargo with an HTTP personal access token to communicate with our GitLab GitOps repository. Using a single HTTPS token with write repository and API scopes allow Kargo to clone the repository, commit updated image tags, push changes, and automatically open merge requests in GitLab for production releases. I already went ahead and created a personal access token called Kargo-service-CI. and it has the right repository and API scope. Third is acr-credentials-secret.yaml labeled with cargo.acuity.io/cred-type is image. These credentials allow Kargo to pull Azure Container Registry. Notice that we use a regular expression pattern for repo URL. This means one single credential covers image tag discovery for all four of our microservices: UI, catalog, recommendation, and review service. This token is the password one which we generated for our ACR. And I copied the same password and updated here in our secret file. Fourth is project-config.yaml, which defines our project level promotion policies. Here, auto promotion enable is set to true across dev, UAT, and prod. This enables continuous delivery. As soon as a new freight is enabled or verified in an upstream stage, Kargo automatically kicks off promotion to next environment. Even though auto promotion is enabled for prod, production promotion creates a GitLab merge request rather than committing directly to main, ensuring human approval remains mandatory. Finally, we have warehouse.yaml. The warehouse is responsible for watching artifact sources and packaging them into immutable release artifacts called freight. Our warehouse subscribes to changes to Helm charts in the charts directory of our GitOps repo. New container image tags published to ACR for our 4 microservices using semver tag matching. When a new commit or image tag is detected, the warehouse bundles them together into a new unit of freight ready to move through the pipeline. Now let's examine how each environment process and promote freight using Kargo stage resources. In the dev stage, freight is sourced directly from the warehouse because our CI pipeline updates dev values directly upon build completion. Kargo doesn't need to write to Git here. Its job is to trigger argocd-update to sync the TrailHead-dev argocd application and verify component health. Once healthy, this freight becomes eligible for UAT. The UAT stage subscribes to freight that has successfully passed dev. Its promotion template runs an automated multi-step pipeline. Git clone the GitOps repository, YAML update to patch updated microservice image tags in environment/uat/app/values.yaml, and git commit and push the changes to main, and argocd update to trigger deployment on TrailHead-UAT namespace. Crucially, UAT includes an analysis verification step referencing analysis-template.yaml. This automatically runs a Kubernetes container job that tests in-cluster HTTP endpoints for all services and validates full Postgres database write and read round trips. Freight only advances if this mock test passes. The prod stage receives freight that has passed UAT verification. For production, Kargo enforces an enterprise GitOps approval workflow. It updates environment/prod/app/values.yaml file on a separate target branch. It uses the git-open-pr to automatically create a GitLab merge request targeting main with detailed release notes listing all included image tags. It uses git-wait-for-pr to pause execution until a human team member receives and merges the merge request. Once merged, it notifies argocd to complete the deployment. To bring this entire GitOps pipeline to life, we apply this manifest using kubectl. Applying these Kargo manifests along with the argocd app project and root app manifest applied earlier is a one-time platform setup. Once applied, Kargo and argocd run completely automatically in response to new commits and container image builds. Let's apply all platform manifest and stage definitions now. Let's open our terminal and navigate into env-config-gitops repo. If we head over to the Kargo UI, we currently don't have any projects. Let's go ahead and first create a project by applying the project.yaml file under platform/Kargo. I will run kubectl apply -f platform/Kargo/project.yaml. Let's hit enter. This will go ahead and create a project. and the project TrailHead is created successfully. If we head over to our Kargo, let me refresh, and we have the TrailHead project. Next, let us go ahead and create the GitLab repo creds. I will run kubectl apply platform cargo gitlab-repo-creds.yaml. Let's hit enter. This will go ahead and create our secret. And the secret TrailHead GitOps repo cred is created successfully. If we head back and click on TrailHead and click on the settings and navigate to secrets, and we should see the TrailHead-GitOps repo creds created successfully. And this is the URL for our GitOps repository, env-config-gitops. Let's head back. Next, we're going to create the ACR credentials. Replace the GitLab with the ACR credentials secret.yaml file. Let's hit enter. All right, the secret TrailHead-ACR creds is created. We head back, and if we go ahead and refresh the page again, so we have two secrets now, one for our ACR, the other one for our GitOps repo. Now, let's go ahead and apply the project config.yaml. Finally, apply the warehouse.yaml. And it is done. We could see that our warehouse is successfully created. Now we're going to apply the environment stages and UAT smoke test verification. First, I will run the kubectl apply -f environment /dev/platform /cargo stage.yaml. Let's hit enter. So this will be for our dev stage. So if we head back and we'll give it a second for it to refresh. So we have our dev stage. Next, let us go ahead and apply the cargo stage for our UAT platform by running the kubectl apply command again. I will run kubectl apply -f environments UAT/platform /cargo stage.yaml. Next, let us go ahead and do the same thing for the prod. And finally, we will apply the smoke test analysis template for UAT. I will run kubectl apply -f environments UAT platform /analysis template.yaml. Let's hit enter. With all manifests applied, Kargo is now active, and it will automatically begin discovering freight from our warehouse and promoting releases smoothly from dev to UAT and opening production merge request. And here is our project. 3 stages laid out left to right exactly like the diagram. Dev already lit up because that catalog service image we just pushed already landed there. Kargo's warehouse independently noticed the same new image in ACR that our CI pipeline wrote into Git and confirmed dev is healthy with it. And look, UAT already picked it up too automatically because UAT's promotion policy is set to auto-promote once freight verification healthy in dev. Let's watch that actually happen from scratch through so you see every step, not just the end state. Let's trace exactly what Kargo did to get this image into UAT. Let's click on promotion and let's select the promotion name. Here, the promotion Kargo just ran. Step 1, clones the GitOps repo. Step 2, and this is the interesting one, it updates the environment /UAT/app/values.yaml with the exact image tag that was verified in dev, using an expression that pulls the tag directly off the warehouse own record of that image, not a guess, not a hard-coded string. Step 3, commit that changes directly to main, and step 4 pushes that change, and step 5 tells Argocd to sync UAT against that new commit. One more thing worth showing, UAT doesn't just promote and hope. There is a verification step attached to this stage, an automated smoke test that actually hits the running services in UAT, confirms review service can write to and read from the real Postgres database, confirms the storefront can reach all 3 backend services. If that smoke test fails, this freight gets marked unhealthy right here in UAT, and it never becomes a candidate for prod. That's a real automated gate, not just a green checkmark for its own sake. Here is where the story changes. Prod's promotion policy is also set to auto-attempt. Kargo doesn't sit around waiting for someone to click a button to even start the process. But watch what promotion actually means for prod. It's not a direct commit like UAT got, it's a merge request. In our env config GitOps repo, let us click on the merge requests. There it is. opened automatically by Kargo. The moment Freight verified health in UAT, look at the description. Kargo wrote out exactly what's changing, every service, current version, proposed version. This is a full human-readable change request generated with zero manual effort, sitting exactly where your team already reviews code, GitLab's merge request UI. With your existing approval rules, your existing required reviewer settings, all of it unchanged. If you click on the changes, this is the values.yaml file change, same shaped as the UAT commit, just sitting in a PR instead of landing directly. This is the one deliberate manual step in this entire pipeline, from commit to production. Everything before this point, building, testing, scanning, dev UAT, fully automatic. This right here is where a human looks at exactly what's about to change in front of real customers and makes a call. I'm going to go ahead and approve this merge request. I'll click on approve, which is optional because we have a single approver. Then let us go ahead and click on merge. And the moment that merge lands, Kargo, which has been sitting here waiting on exactly this merge request, picks it back up automatically and finishes the job, tells Argocd to sync promotion against the new commit. And if you head back to our TrailHead prod service, application is synchronizing now and it is updated and the app health is progressing. Once the sync is healthy, we'll go ahead and try to access our production environment using the load balancer IP and verify that our changes are propagated from our dev to our production. Our application rollout is successful in production environment. We can list all the services in our production environment by running the kubectl get svc in the namespace TrailHead prod, and the TrailHead prod UI service is currently exposed using a load balancer service, but in production it is recommended to use an ingress. So we already have the configuration in our app values.yaml file, but it is currently disabled. So you can go ahead and install an ingress controller and enable these flags, so customer will be able to access using something like www.trailhead.example.com. Now let us go ahead and copy the load balancer IP, head over to a browser, try to access our application using http:// then the load balancer IP, and there it is. The exact same changes we made back, one line of product copy, just walked itself automatically through building, scanning dev, and automated smoke test in UAT. A human reviewed merge request and landed in production. One Git push, one human approval, and a complete permanent record in Git of every single step in between. That is what production ready actually looks like. Not fast, not fully automatic everywhere, appropriately automatic, fast where speed is safe, and gated where it isn't. Last piece. Deploying safely is off the job. Knowing when something actually wrong is the other off. We have got Prometheus watching every environment with alerting rules that don't even require our service to expose custom metrics to be useful. For crash loop back off, deployment with unavailable replicas, our review database disk getting full. These filters of Kubernetes own metrics, which means they work on day one before single team has instrumented a line of business logic. That's the last safety net in this whole system. Even if something changes outside of Git, by accident or by hand, Argocd is going to notice and Argocd is going to fix it. That's the GitOps promise all the way through. Git isn't documentation of what's running, it is what's running. If you followed along and built this yourself, genuinely well done. That's not a small thing. You just built the same shape of platform that real engineering teams run real revenue through. And you understand why every piece is there, not just how to copy the command. Everything in this video, the app, the Terraform, the Helm charts, and GitLab CI pipeline, every Kargo stage is linked in the description below. So you can pull it apart, break it, and rebuild it, which honestly is the fastest way to actually learn this stuff. If this helped you, the actual best thing you can do is go try it, break something on purpose, and figure out how to fix it. That's where this stuff actually sticks. If you found this video helpful, please do not forget to give this video a like and subscribe. It does really make a difference to this channel. Thanks for watching, and I will see you in the next one.